that if you're going to use wick drains, they're well established, and in fact, the current version of wick drains, once again, there's the drain, and then we have the filter sleeve, if you like. So drain going into filter sleeve. This is really simply, I'll call it a polymeric, a geosynthetic version of what was used prior to the advent of the polymeric wick drains. And prior to that, it was the installation of sand drains. You would auger a hole and sometimes put down a cardboard tube and then fill it with sand. And that dates back to the 1930s, 1940s. So in terms of installing vertical drains to accelerate consolidation, let's say the learning objective number one is to recognize that the design guidance is long-standing, and we'll look at its evolution over time. That's learning objective number one. So that's good. We've got a decision support tool in our toolkit in the form of design guidance, and indeed you can either spreadsheet it up, as I ended up doing on one project, or I think these days you can get commercially available software. So we have a design tool in our toolkit. How confident, here's learning objective number two, is how confident can we be in the design decision support tool absolutely nailing the future performance of the structure? And that's a key learning objective, and we'll look at that from the Vernon Bridge abutment. We'll look at it from the mine waste tailings, and then I'm going to also pull from ASCE a wonderful case study that Tim Stark published about 2 years ago in ASCE. It's actually quite instructive as well. So learning objective number two, how confident can we be that having used the design guidance, we'll nail the future performance of the structure? And then the third learning objective, by going through a sensitivity analysis to field observations at the Vernon structure, we can then say, where should we be putting, we've got a finite amount of time in design, where should we be putting our greatest effort and giving the greatest consideration so that our use of design guidance is likely to produce a prediction of performance that will likely be close to the observed performance. Okay, so that's kind of the bundles of the learning objectives, and I'll call those practice-oriented observations. With that setting the scene, let me move to here. And I guess actually I should start recording the lecture. I'm going to have to come out of here and I'll start recording the lecture.
This meeting is being recorded.
Okay. So, on the subject of prefabricated vertical drains, and when we talk about prefabricated vertical drains, we're talking about a drain that looks like this. They're not all made exactly the same, but if I turn up the corner here, you can see that kind of corrugated look to it. So I'm going to capture that corrugated look, and I'm going to capture that here. Let's put in the corrugated central core. Let's put that like that. And that core, the core that we're seeing here, that core is then surrounded by a filter. Okay, there's the filter sleeve, and it's a little tricky actually to push it all together. All the fibers inside tend to impede the core going into it. Let's see if I can get that all together, and there we have it. There is the drain, arguably the porous medium of the central core, and it's wrapped in the filter. So let's put a filter around the outside. I'm going to schematically show the filter as a little bit of a interwoven. It's a non-woven filter. So that's what I'm attempting to capture with this cartoon-like image. It's actually a heat-bonded non-woven. So there's our core. Let's call this the drainage core. And here is the filter. And typically, I guess because it's relatively inexpensive amongst other things, it is a non-woven geotextile. And in fact, it's a heat bonded. By heat bonded, we mean that the fibers, and you can see it here, the fibers, they're the individual fibers, aren't they incredibly small? And the individual fibers have been laid down and then passed between two heated rollers and essentially compressed together. It tends to produce a side that's quite glossy. It's on the inside here. You can see the opening size distribution there actually quite nicely. Tends to produce a very thin, somewhat glossy feel to it actually. It's got feels very slippy to the touch, and tends to be a little hydrophobic actually. So were I to pour water on this, I got another one here. Actually, this is from a particular project, but it's that's just the geotextile itself, and it's quite glossy, it's almost got a little hydrophobic nature to it. If I was to pour some water on here, it would bead and run off. And in fact, that's one reason why highways folks tend not to promote the use of heat bonded non-wovens in, I'll call it near surface alternating wetting and drying applications, just because of this tendency for water to pond on it a little bit. But that's less of an issue, I've got to tell you, and we'll see in some photos that once you shove it into the ground and it gets saturated up very quickly and remains saturated, then it works just fine. It works just fine. So there's our prefabricated drain, and it's installed in the ground. And to show you the installation in the ground, I think I'm going to, hopefully this works, because we can drop that. I think we can drop that for now. And let me go and share this screen now. Bear with me. Oh, I seem to have lost you guys. No, thank you for your patience. Okay. Now I think. Do you see the Keller screen that I'm showing there? Excellent, thank you. So I think you can access this from YouTube, but it's quite a neat little video, and let's play it. It goes very, very, very swiftly. So we have the wick. Oh, it's gone extremely swiftly. Let's start it again from the beginning and pause it just momentarily. So the wick drain is on a roll here. There's probably 1,000 feet of it on this roll, and it gets taken up and over the top here, and then it's deployed by this mandrel, pushing it into the ground. It has a little let's see it pushed into the ground. Bingo, there it goes. Let's see another one. And I'll try and stop it. Oh, there we go. And you capture it, you wrap it around a little steel plate here. It's like an arrowhead by the time it's finished, I guess. But you drive the mandrel down, you wrap this little steel, just tiny, tiny flexible steel plate over the end of the drain, and it gets pushed down, and then when you withdraw the mandrel, it just acts as a fish hook to hold it at the base. You pull up the mandrel and then cut it at the ground surface and do the next one. You can probably put them in 1 minute or something like that, depending on how soft the soil is and whether you have to pre-auger. So now you've got this vertical forest of prefabricated wick drains, and then come along, place the embankment, if that's the application we're looking at. I'll let it continue. The embankment settles. Do you see the embankment settlement there? And that's taking place as we expel water, groundwater, up through the drains, and the volume change by expelling the groundwater is associated with the settlement, assuming we've got no significant lateral spreading. And the idea is that you can accelerate the consolidation settlement owing to the presence of the wick drains. Okay, so that's the nature of the application. And if we capture that, bear with me, I want to go to here. Fantastic. So if we capture that arrangement, we have this core, the sleeve of the plastic fabric. I'm going to strike out they may be the same material throughout. That was true perhaps in the early days, and there were a number of variations, but the nature of things has now pretty much consolidated, no pun intended, into the arrangement that we have here. And we drive these into the ground. So let's drive the wick drain into the ground, as we saw in the video there, and that will produce a wick drain here, another wick drain here, and the intent is let's have the soft ground. I'm going to represent a number of little lenses in the soft ground, however they got there. And our intent here now, when we come along and surcharge the system, if it already has considerable strength, if it's mine waste tailings and we're trying to dewater it or remove leachate from it, we may be able to achieve that just under the self-weight loading of what is in essence a slurry. But if we have firmish ground, soft ground, then applying the surcharge is going to generate excess pore water pressures. And those excess pore water pressures will dissipate, and the path of least resistance, arguably, is going to be to the drains. And in the absence of drains, let's look at the case of with the absence of drains, then the excess pore pressure is going to drain upwards, for sure, to the free surface. And it may or may not drain downwards, depending on what is the stratum at depth. If we had a sand stratum of depth, of course, it could drain downwards as well. So the expectation, the system response is such that this will accelerate the consolidation settlement. The function of the central core is this free draining channel. Sometimes they may even have little holes drilled across them from side to side to promote the unimpeded flow of water through the drain. But we're anticipating that we're got this free draining, the filter on the outside, the filter fabric. You know, I should really get away from that phrase. Let's be quite correct. The geotextile filter, odds on it's going to be a geotextile. The geotextile filter is preventing the drain from clogging with material washing into it. And if properly evaluated, the geotextile filter itself shouldn't clog. And thus we get this anticipated increased rate of consolidation. That increased rate of consolidation generates an associated increased rate and gain of shear strength. And were we to have significant lenses in here, then pockets of potentially elevated excess pore pressures will be drained, in essence, preferentially drained as well. But it's this consolidation settlement and this gain in strength. Those are the rewards, those are the benefits, those are the return on the investment of time and effort. And in essence, in dewatering tailings, we want to ensure that this will take place. And the question might be, that generally how long the drain should be is fairly self-evident, but the number of drains is going to be driven by their spacing. The drain spacing. Center to center drain spacing. And in essence, we're going to try and correlate the spacing of the drains to the time to achieve a certain percentage, okay, of consolidation settlement. And over the course of that settlement, gain the increase in shear strength. That's our system, okay? And if I was to illustrate that system and show you what it would look like at the ground surface, here is that. I can't quite see it. Oh yeah, there. Yeah. So here's the wick drain being taken up to the top of the mandrel, coming down. And this is this little steel plate that I was talking about here. The drain gets hooked around that plate really easily. So there's our rotated around the end, and then that gets driven into the ground. The plate is sacrificial, stays at the bottom. Withdraw the mandrel, and you end up in at the ground surface with something that looks like this: the filter cloth or geotextile filter and the drainage core in the middle, as we see it here. And there's one there, there's one there. Doesn't look like there are many others in the photo. When the mandrel gets withdrawn, whoever's in the field is maybe just going to bring a pair of simple clippers and cut it and move on to the next one. So that's our arrangement for getting it into the ground, and the consequence of that is going to be, let's move from this image to this image. There's one, there's one, there's one, there's one. So we're going to put them in the ground, and we can put them in a square, but more often it tends to be a triangular pattern. Okay, and the drainage is going to be radially towards the wick drain. Okay, radial drainage towards the wick drain. Radial drainage towards the wick drain. So if we have a drain spacing, then we can correlate the diameter of the equivalent cylinder of soil that's being drained. If you imagine a bunch of cylinders all around each other, if it's a triangular variation, then this equivalent cylinder that's being drained, and this is going to come into our design. This is an input to our design. If DE is a function of the physical spacing D. So for example, if it's a triangular one, we can do the math and we establish this relation here. And if that holds true, then for example, if we were to put them in the ground at a spacing of about 1.2 meters, and I think I'd choose that because that number is going to be relevant to one of the studies we'll look at. If that's the case, it doesn't make a huge difference. This results in DE being approximately 5% larger. Therefore, DE about 1.26 meters. So it doesn't make a big difference. We're not going to get too worried about this, and I'll tell you why. Because we're presupposing here now that this forest. Do you remember the little animated video? And we had this forest of PVDs. They'd gone in, and they were all beautifully parallel to each other. But if we flick forward some pages in the notes, let me take you to the case history that we'll look at. And here is a plan view and a cross section through a fill. And it's one thing, I'll start on the left-hand side here. This is 12 meters high. The drains here were installed to a depth of 24 meters, so I'm going to go twice the height of the fill. And so can you imagine, I'm going to draw them, and 1/12 of this might be about the spacing. There's that 1.2 meter spacing, 24 meters in length. So let's take it about 1/10 of this. And now if we actually try to represent the wick drains, we would be doing something like this. And clearly, I'm going to start going a little bit off the vertical, quite deliberately, because these are not going to go in perfectly vertical. We're going to end up with something that looks like this. We might be aiming for this, but by the time you're getting it to depth and driving something that's a meter apart, 24 meters into the ground, they're going to be all over the place. So let's go through, finish this off, because it will serve us a little bit later in the lecture. Let's call that our schematic arrangement. of a bunch of drains at a triangular pattern with 1.2 meter spacing to a depth of 24 meters. So for those reasons, that's why I'm not going to get too bent out of shape if we turn back to here and say, look, okay, I take the relation, I get that DE is equal to this, but you know, I'm not buying into it being an absolute constant separation over the full length of the drain. Now, what are we expecting? What are we expecting these drains to do? And Bengt Felenius, a number of years ago now, carried out actually what I thought was quite a neat little study, and it sets out what the drains are going to do for us, right? It was a parametric, very simple, but sometimes these are quite instructive. He took an oil drum, let's put the oil drum here. The oil drum had a drain in the middle of it. In fact, he set an arrangement up with 3 different drains, M, G, and A. Let's put the drain in the middle of the drum. Drain M, the geometry of drain M was 50 millimeters by 7 millimeters. That's relatively thick. And drain G was 100 by 3, not far off common dimensions. And the last one, 100 by 7, was quite chunky. And also had one setup, and it was no drain, just the remolded clay compacted into the oil drum. And then to facilitate consolidation, a surcharge load was applied. And that surcharge load was relatively light at 10 kPa. But that caused consolidation radially and out of the drain. And Felenius and co-worker reports the degree of consolidation, or the consolidation ratio, uppercase U bar, that they defined with regard to, let's turn this here, the consolidation ratio they defined with regard to settlement. Okay. So the consolidation ratio, U bar, is equal to the settlement at any time. I'm going to give settlement this symbol here because it's useful for future notes coming up from another reference, over the ultimate settlement or final settlement, but let's call this current settlement. As a function of final settlement. We could also express this, but I don't believe the measurements were taken in terms of excess pore water pressure or mean excess pore water pressure at the current time, non-dimensionalized by the initial excess pore water pressure. That the commitment to measure that is quite significant. Commitment and get it reliably. The commitment to measure this is less so. And what we observe is a little almost microcosm of what's happening in the field. The three drains, the degree of consolidation is relatively insensitive to the drains. The drains provide more than adequate capacity. And in contrast to the no drain, which is what we have here, at any particular elapsed time, this much greater, faster consolidation and with that commensurate gain in strength with the drained using the prefabricated vertical drain versus the undrained. And often what we're seeking is to accelerate the time, for example, to achieve 90% consolidation. This is often what we're looking at is the time to achieve 90% consolidation. The time to U bar equals 0.9 or 90%. Okay, and that's what we want to accelerate. Without the drain, this would be way out here, and in the presence of the drain, it occurs much more rapidly. Okay, so there's a nice, I'll call it, what do we want to call that? Kind of almost a representative element test. And it works. Let me take you to this report that was produced. It's just a very nice summary of what happened at the Alex Fraser Bridge. It's a suburb essentially of Vancouver in the Tri-Cities, and wick drains were installed. The wick drains were installed, excuse me, to a depth of 17 meters. Wick drains were installed to a depth of 17 meters. There's our 17 meters from a working platform. And as a consequence of that, the settlement period, excuse me, the settlement period was reduced to months instead of years. And that was the argument for installing the wick drains. And the quantity was huge. If we come back up here, $1.3 million meters, 1,300 kilometers. Of wick drains installed as a part of the bridge approach. Okay, so excuse me, considerable use of them. And I want to just alert you to, that's the bridge abutment or a bridge approach. We'll actually do a forensic analysis of one near Vernon. But I wanted to also alert you to the mining world. And it was neat to go around the room at the beginning. I pulled this off the web. And you could go to Keller. If you do a search for Suncor Pond 5 wick drains, you too could pull this up. In fact, that's where you're going to get that little Keller video as well. And the arrangement that was used there was to put out, it was all about capping to keep permitting going. And there have been a number of publications written on it. Here's a nice photo. It shows the wick drains installed into the fine tailings, MFT, mature fine tailings. And can you see here? Do you see? Look, there's no surcharge load or anything, but even just the self-weight consolidation has driven the fluid, the pore fluid up, and it's actually spilling over and spilling over. And you can see it again over here. There's standing fluid inside the sheath of the prefabricated vertical drain. That's what I was talking about, that it takes a while for it to saturate up. But literally, as they're being installed, they're starting to produce fluid as a consequence of consolidation out of them. And the numbers are just staggering. If we take a look at the 1,300 kilometers that went in at the Alex Fraser Bridge, if you scroll down on that Suncor Pond 5, it was 6.2 linear meters, 6.2 million linear meters, almost 5 times that, 6,000 plus kilometers of wick drains installed there. And I remember, chatting with at the time of seeking bids on the work, and there was a nice write-up. Sean Wells at Suncor, Jack Caldwell with Robertson Geoconsultants, they wrote up a nice little, for those of you that are interested, the vertical wick drains acceleration. And they spoke to the work, the lab testing that we did at UBC. And the lab testing done at UBC was to establish if the geotextile filter, here's an example of one of the filters we actually examined in testing, was it going to clog? Might it clog when the pore fluid, and it's got hydrocarbons in it, it's got bitumen in it, might that clog? And that was a serious concern. I remember chatting with the with potential suppliers for the wick drains, because we had to solicit the geotextiles ahead of the job, and we tested them. Okay, that's what these guys are alluding to in the paper here. And we had the tailings supplied to us, and we ran gradient ratio type of tests. Not quite gradient ratio tests, but we ran rigid ball permeameter tests. The lab test provided the following general conclusions. There was no evidence of clogging of the heat-bonded non-wovens with opening sizes in the 90 to 210 microns. We opened it up a little bit more and we had a woven geotextile. We could indeed have tailings piping through the geotextile. That was a nice confidence builder. That was the piece of the puzzle we worked on. And then it went to construction and the 6.2 million meters. But the point I wanted to share with you was that the fabricators, the geosynthetics fabricators of the wick drains said to us, on a job of this size, we will put any geotextile you want around that wick drain. If we need to custom make a geotextile filter, turns out they didn't need to, but if you need to custom make a geotextile filter to go around it, we'll do that for you. And that gave me just a good sense of the commitment to getting it right. Okay, so interim summary. Remember, the first thing to do was learning objective was to look at how they work and a little bit of the historical origins of current design practice, current decision support tools. So let's look at these these drainage characteristics. What are we expecting our decision support tool to embed in it? And the first one is going to be, we have a drain that looks like this. It has a finite width and it has a finite thickness. And we're actually going to treat it as an equivalent circular drain with some kind of diameter. And because I work through a couple of different reference documents, we may find symbols jumping around a little bit, but let me try to be systematic. A diameter, equivalent diameter of the equivalent circular drain, because that's the way we're going to do it. We're going to have this in the middle of a 1.2 meter, for example, triangular spacing and radial drainage to it. And then there's the physical spacing in the field, likely triangular, and that's giving us the actual physical distance or separation. And when we install it in the field, this may end up, can you imagine? Let me go back and pull up one of the photos here. Probably not so much of an issue here because it's such a remolded material in those mine waste tailings. But if we're in soft ground, can you imagine that when you drive this down into the ground and then you withdraw the mandrel, you'll likely have remolded and reworked a bunch of material around the outside. So have we, installing this, have we disturbed the soil? Have we remolded a zone around? And if we have, has that changed the hydraulic conductivity of a part of the system? And that we're going to model. Let's put our drain here. And actually, we're going to model that as an equivalent circular zone of remolded material. And we're going to have to give that some kind of designation. Let's give it an equivalent diameter, and we'll give it S for soil disturbance, or the phrase that's used in design jargon is smear. And then there's a question of whether or not the drain itself offers resistance to flow. How free-flowing is our drain? I've drawn it horizontally. And this includes, for example, and you know, I'll try to illustrate it here. Can you imagine you've installed this? Maybe it's a little off vertical, maybe it's beautifully vertically. And then you have consolidation settlement. In that Vernon location with the length of the drains that were 24 meters, there were 3 meters plus of settlement, an enormous settlement. And can you imagine what that's doing? As I'm going to try and hold it relatively thin. Actually, let me pull the drainage medium out of the core. It's going to make things a little evident. There's our drainage medium. And now I got to get I'm trying to compress it. We're trying to get 3 meters of consolidation settlement going on. And can you imagine what that drain is going to look like after it's been compressed, settled, maybe folded over to accommodate 3 meters of settlement? So drain resistance within the drain, but also because of a change in the alignment of the drain. And then finally, there's I'm going to call it the let's do this differently. Let's call it the geotextile, because odds on it is going to be a geotextile filter jacket, and we want some filter compatibility. Okay. Bear with me while I think that pencil has died on me. We may move to, and so there's a question of filter compatibility, and that's what we were addressing in that study for the mine waste tailings. So first up, let's pick these off and let's just go through them. The equivalent diameter of the drain, number one, we're going to go 1, 2, 3, 4, 5. Equivalent diameter of the drain. Here's the drain. Here's our equivalent diameter. And DE is equal to, let's say, B is 100 millimeters. Let's say the thickness T is 3 millimeters, right? Not far off the geometry that we have in this combination here. And DE is going to equal about 65 millimeters or so. Okay, and in terms of spacing, odds on we're going to have a triangular spacing. Each drain has a zone of circular influence. 1.05 times D, spacing D. If that's true, that's going to hold. In our analysis, just to come up, or our derivation of an expression, we're going to make a number of assumptions regarding volumetric deformations and excess pore pressures and underlying assumptions of permeability and Darcy's law being valid, notwithstanding these being relatively low permeability soils. I can add one here. No change in the hydraulic conductivity of the soil, either undisturbed or remolded. In the assumptions. And if we do this, I'm going to a little look ahead. There's going to be three cases that we'll look at for design. One is the nominal ideal scenario. So no change in the hydraulic conductivity of the soil as a consequence due to consolidation. And no annulus of disturbed soil. And I'm going to capture this phrase again, due to smear. Okay. And this combination is what we would call the ideal case. Let's go in here. I'm going to capture the nose. So no disturbed soil. Permeability of the drain is infinite. I'm going to say effectively no resistance in the drain. And this combination of no resistance in the drain and no annulus of soil, we'll call that the ideal case. And this is going to be one of three cases that we'll look at. The ideal case, then the next case is going to be, well, what if we happen to have this function of just soil disturbance? And then the third case is going to be, what if we have drain resistance that we can't ignore for one reason or another? So we're setting up terminology. Interim summary, how are we simplifying the system? How are we modeling the system? What's the conceptual model for the system? How do we put some numbers onto these conceptual parameters? And how do we conceive of a number of cases to analyze? And that's going to form part of our sensitivity analysis at the Vernon scenario. So with that, now let's jump into a little bit of math. Okay, and the math is going to be a derivation of an expression. It follows over the page. I wanted to remember that learning objective of how far back do we go? The general approach for vertical drains, and it's set out here, was picking up on Tertzagi's appreciation for time factors governing consolidation or degree of consolidation. There it is again, captured with regard to settlements. Okay, but it could be done with regard to excess pore pressures, and that in fact is the derivation that we're going to look at just over the page. But we go back to Tertzagi, and then another player at that time was Barron, and this was in the 1940s. So Barron took Tertzagi's concepts and came through and said, listen, I can look at the degree of consolidation, okay, I can look at the degree of consolidation due to horizontal drainage, not Tertzagi's one-dimensional vertical drainage, but Barron took the concepts and looked at radial drainage, and radial drainage only, to the complete setting aside any small contribution from vertical drainage. And that can be expressed, see the way this one was expressed with regard to settlement. This one can be expressed with regard to settlement, or shown here with regard to excess pore pressures, okay? I'm going to put a little, I'm going to leave it without little bars on it, but we'll see when we go over the page, right? So what we're doing is we're looking at the degree of consolidation due to radial drainage only. And if I went up top here, I could put in a generic expression or a generalized expression. That the overall degree of consolidation is a function of that arising from horizontal and that arising from vertical. And we can look at ignoring the horizontal and only consider vertical consolidation. That's what Tertzagi is doing here. We can ignore the vertical and only look at horizontal, and that's what Barron is doing in his solution. We can express the degree of consolidation either in terms of settlement, or we can do it with regard to excess pore pressures. We could indeed do it also with regard to changes in void ratio and or changes in effective stress. There's a number of ways we can define the degree of consolidation. Now let's put Barron to one side. It will his work will float through, but this is the key derivation from modern design practice, and that came in the 1970s. It was a slight variation to Barron's work, because Barron was actually, he had strictly circular drains. They were sand drains. Hansbo, this Swedish guy, reworked things a little bit, and I'd like to take you through Hansbo's derivation. It's going to take us down to what we see at the bottom here, and I'm going to look at our exit and then take us back up. So we have the degree of consolidation due to radial drainage only, correlated to a time factor, where the time factor itself is a function of time, t. And this is really what we want, the relation between these two, okay? And we've seen it already. Let's not forget it. Let's go back to Frobenius's work, and there it is, experimentally. The relation between the degree of consolidation and time. The relation between the degree of consolidation and time, okay? And out of this, we can manipulate this expression. This is our final parking spot, is the time. That's what we want, the time. Out of this, and we'll see where it's coming from, is equal to the equivalent diameter over 8 times C sub h. We're going to have a mathematical function of a ratio. Okay, and that gives us again what we're after. There is this, and there is our time. The time to achieve a certain degree of consolidation is controlled by this. Okay, so let's look at where our, I'm going to call it our tool, our descriptor of that experimental observation of Frobenius comes from. This n, let's go back up, and I'm going to decompose this derivation here. That's going to cause me to jump in at a couple of places. So bear with me while I do that. N, okay, is equal to d over d. Let's take that out. That is a geometric design ratio. According to Hansbo's use of terms, it would be d over d. And what we set things up a little earlier is dE over dE. The equivalent diameter of the drain and the equivalent cylinder being drained, which is as good as the triangular spacing. Okay. Now, what's happening? Let me describe what's happening, and that will then allow us to jump into the derivation. Okay. Here is, if I was to look at it from a surface point of view, there's the equivalent circular drain, and this is looking at the equivalent cylinder that's being drained. Okay, so we have radial drainage into this central annulus. Okay. And what we have is cross-section all the way through. And in that cross-section, let me shade what would be the draining material. So there's the soil. That's the soil that's draining radially into our equivalent diameter. of the prefabricated vertical drain. Okay, and let's imagine that we have some kind of surface across which we're going to examine the flow across that surface towards the drain and the volume change. The volume change, and that's where our settlement is going to be coming from, the volume change associated with the flow. Okay. Volume change associated with radial drainage into the drain is causing consolidation settlement. And there's a bunch of assumptions, and then it's just connecting the assumptions, okay? So let me box the assumptions for you. First up, Darcy's law. That's an assumption. Then let's look at this flow and volume change. There's another assumption, and let's box that. Here's another assumption. Let's box that. Okay, that the inflow of pore water through the boundary, this is the boundary that I was speaking about here, is equal to the change in volume of the hollow cylinder that's outside it at some nominal radius. Okay, that's that bit. And then there's another, it's almost by definition. Okay, let's look at the average excess pore pressure throughout the soil cylinder, and we define it. This holds true. This is a reasonable assumption. This is by definition. And then there's a third one by definition, and it's just to do with a compression modulus and a rate of change of excess pore pressure with time. And time we want to get in here, or Hanspo wants to get in here. So we have this, and arguably we have this definition of this geometric design ratio. So what we're really doing now is bridging between these assumptions and definitions. We'll set them there. There's an assumption, a definition, and a further definition. Okay, now let's work our way through, and we start with the hydraulic gradient and a change or a difference in excess pore water pressure, delta U. And we can take that delta U and we take it down here and we continue to follow an expression for delta U, which we then relate to the excess pore water pressure U, and then the mean excess pore pressure U. Which gets restated here, now introducing time. Okay. And then by restatement, degree of consolidation. This is just reworking this. Okay. So if we look at the logical flow of the derivation, it all starts with Darcy's law. Darcy's law is valid. And then by looking at it in terms of flow and volume change, and bringing in a compression modulus and bringing in time, we get an expression here, and restating this, in essence, becomes this. And this is what we want. This is what we want in any design situation. And if we want to achieve a certain degree of consolidation in a certain target period of time, we're odds on going to manipulate the spacing of the drains to get that, okay? And this function here is where, let's take this out. This function will vary depending on whether we're looking at a function that's describing the ideal case. Remember that ideal case with no smear and no drain resistance, or whether we're going to consider smear and or drain resistance. Okay. So now we've set ourselves up. And this is a derivation that follows Hansbo's work. Okay. Let's go back. Hansbo did this in the 1970s. And revisited actually in a symposium in print for Geotechnical in the early 1980s, but after Hansbo. Okay, now I do have some additional notes that you have here, and we can skip through those relatively quickly because this is the equation we want, and we can pick this up, okay? So in terms of the learning objective of the origins of it, were we to go back to Barron's work, this is now returning to Barron's work. There, this is following on the description of the original work, but here's Hansbo. Hansbo modified the equations developed by Barron for prefabricated wick drains using the same approach, but his modifications dealt with some simplifying assumptions, okay? So everything that's following here, this is from Hansbo and then we flip back to Barron over here. So I just want you to get this feeling that, okay, Barron was working in the background with perfect cylindrical drains. Hansbo came along and modified it, and this is the equation we want to be picking up on. And that equation is what we're going to, this equation is what we're going to take to the case study, okay? And if I set the scene for that, bear with me, I just want to check my there we go. Okay, that equation, if you jump forward into almost the tail end of the notes, we have an expression, and this function of n is being captured. This is what I wanted to do. See this being captured now here. This function of n is being captured by mu. Okay. Apologies for the evolution of symbols throughout the notes, but it's because of working to multiple sources. Okay. Okay. So, interim summary. Hansbo does his work in the 30s, 40s. Wick drains clearly work. Hansbo comes along, gives us this derivation, a relation between time and degree of consolidation, given the nature of the soil, given the spacing of the drains, and a function that's taking account of assumptions as to how much additional disturbance and impedance may arise from the drain itself. Okay, and that's transpose derivation, and we have in the background it running in parallel. But actually, I could almost cut those pages of notes, and indeed I might do for next year, because it's probably overkill. That brings us to seeing how good Hansbo's equation is. Okay, how good is Hansbo's equation? And here I was privileged. I have to acknowledge this was back in 1991, almost 30 years ago, and I was a young, very keen, industry-focused academic, and I shared an office with Carl Crawford. He had retired, and in his retirement, he'd retired from working in Ontario, came out as an adjunct professor at UBC. I shared an office with him for a number of years. We became very good friends. He's now passed away. And in his retirement from practice, Carl Crawford wrote up a case study each year, one a year. And he teamed up with people. And in this case, he teamed up with me, and he teamed up with two fellows at the Ministry of Transportation and Highways, as it was then called. And it was a really neat project, actually. And Carl hunted for neat projects, and he had a strong interest in consolidation over his career, and always struggled with matching design and practice, matching the predicted performance and the measured performance. And Carl was a wonderful guy to work with, and he in turn in his early career had worked closely with, amongst others, Carl Crawford, who was a consultant on a number of projects that Carl was involved with. There's a wonderful story of Ada, his wife, still with us and living in Ontario. And Ada described for me once over dinner dancing with Carl Terzaghi at an international conference in soil mechanics. So now the story of this is interesting. In essence, it's a tale of two embankments, and let's look at those two embankments. The story is written up in a paper to the Canadian Geotechnical Journal. Here are the two embankments. The west abutment, test fill, so-called, because it was going to be abutting to a bridge overpass over the CP rail line, just on the outskirts of Vernon, and the waterline test fill, which was going over a utility. And an embankment was going to be built, and the bypass road and then put in. And the ground conditions, water table was of the order in the upper 2 meters or so. Let's go in and put the groundwater table. And it was an alluvial kind of sand, silt, and clay layer, but underneath that, a little bit of a historic weathered crust, and below that, this soft to firm clay. And this was going to be the challenge. And in that soft to firm clay, if you look at the details, the natural water content, W, over a considerable distance, look at that, from about here, maybe from about here to a depth of 30 meters or so, the natural water content is greater than the liquid limit, right? The natural water content is greater than the liquid limit. And that's going to be challenging. If you think of it, if you remold the material, you're going to have little to no strength, basically. A very a deformation intolerant foundation soil. And so the decision was taken to explore using wick drains. underneath this west abutment test fill. So the west abutment test fill had wick drains. And the waterline test fill had no wick drains. Okay, so that's the tail of the two embankments. They're both resting on this subgrade soil. There's our profile of undrained shear strength with depth from field vein testing. The west abutment had the wick drains to a depth of 24 meters. There's our spacing. vis-a-vis. There's the length of the drains, 24 meters. We'll get to where that comes into our function. Remember that function in the expression. An instrumentation to measure settlements. And that's going to give us a relatively direct route into the coefficient of consolidation. So let's look at settlements in green and pore water pressures. Oops. The settlements are measured from settlement plates, primarily. There were one or two other techniques put in, but settlement plate number 1 to settlement plate number 4. Where are they? Settlement plate number 1, settlement plate number 2, settlement plate number 3, and settlement plate number 4. And then pore water pressure, P1 through P4, and for several depths. Depths A, B, and C. And those were at depths of 4, 10, and 20 meters. And there's P1, there's P2, there's P3, and there's P4. And in principle, we could, but it doesn't work out that easily, get the degree of consolidation from the pore water pressures. So we're interested in settlement, and the measure of the settlement at any time t over the final settlement is going to give us a measure of the degree of consolidation. Okay. Or we could get it from the dissipation of the excess pore water pressure. So let's go in here and look at the initial average excess pore water pressure, how that's going to dissipate with time and ultimately dissipate to 0. And we could look at 1 minus that ratio and get the degree of consolidation from the dissipation of the excess pore pressures. Okay. And we have some lab test data for the foundation soil. And we know that testing provides, let's go in, I'm going to put this somewhere else. Let's go in and put this here, that lab testing established that C sub V was in the range 2/10 and -4 to 2 10 to the negative 3 centimeters per second, centimeters squared per second. Now we're not so much interested in the vertical, we're really interested in the horizontal. Okay. And we'll have to make some assumption there, okay? And bear in mind all the time in the background, and shall we go forwards to it now? We have this expression that T is a function of C sub H, which we don't have, the degree of consolidation, which we're going to infer from field performance measurements, and try to discern the importance of these three functions, the ideal case plus smear, and the ideal case plus smear plus drain resistance. We're going to get to that first. But at the moment, we're taking a time out to look at the field performance data for this tail of two embankments, one with drains and one without with drains. And now let's look at the settlement behavior. Okay. Relatively large settlements under the west abutment fill compared with the waterline fill with no drains. The waterline fill, do you remember the waterline fill is SP3 and SP4. Here is SP3, SP4. That's the waterline fill, no wick drains. And it's our final settlement. I'm going to use the same symbols in the range 0.3 to 0.6 meters. Okay. And if we go and we look at the waterline, sorry, the west abutment fill, SP1 and SP2, it has wick drains. And the final settlement is of the order of 2.5 to maybe 3.5 meters. Enormous settlement. Okay. And if we take those data for SP1 and SP2, if we take the settlement time record and we recast it as settlement against square root of time and use a Taylor construction, Taylor 1948 construction for T90. The time for 90% consolidation. So you get a straight line, you project it forward 1.15, you look at the intercept gives you T90 for SP1, T90, and for SP2, T90 are actually quite close. And it turns out that T90 is about 260 days. So we can come out of here, and I'm going to put 260 there. And I'm going to join those up, and I'm going to say T90 is approximately 260 days. Field observations of settlement. Okay, so that's good. We got T90 is 260 days. Let's take a look at the four water pressures, the piezometric observations. Remember, we can we want to be working with this combination of settlement and what do we learn from the dissipation of the excess port pressures at this location. And this is where the lifetime of experience of Carl Crawford came into play, and what he saw didn't surprise him, but was quite inconsistent with soil mechanics theory. There's a bunch of text at the top, and you can see that. But look, we have the west abutment. With its data, and then with prefabricated drains, and we have the water line fill with no PVD. And interestingly enough, we got very rapid settlement, or sorry, very rapid dissipation of excess pore pressures with the prefabricated vertical drains, and little or no at depth, 10 meters and 20 meters, little or no dissipation of excess pore pressures with depth. And, you know, upon first inspection, you say, well, that's really weird. How come with no wick drains, the consolidation settlement is over, and yet we've got elevated pore pressures? And how come with the wick drains, we have about 260 days for 90% consolidation, and we've got the pore pressures all gone at about 75 days? And this highlights two things, okay? Thing number one that it highlights is you can complete consolidation without dissipating excess pore pressures. And Carl Crawford had seen that in many other sites, attributed it to destructurization, and that's captured in part of the text here. The second thing is, you know, these pore pressure dissipations are relying, and let's go back to our forest of wick drains. They are relying on measurement of pore water pressure, and you have no idea how close or far away is the nearest wick drain. Not down at 20 meters depth with all of these wicks. So the use of pore water pressure data to interpret the behavior of a wick drain embankment, very tricky. Settlement data, very, very useful. Okay, there's a pragmatic take-home message. So we come out of this and we're going to say, you know, the settlement data are key. So what about our equation now? Let's populate it. Theory. After Hansbo. Here is a relation between time and degree of consolidation. We actually know from the settlement records that the time to get 90% consolidation was 260 days at the site. And Hansbo's solution has this function. And the function is dealing with three cases. Case number one is the ideal case. No smear, no drain resistance. There's the ideal case. There's this ratio dE over dE, straight from Hansbo's derivation. In the event that we had, so let's call this the ideal case modified by smear, or this annulus of disturbed soil. So I'm going to call it soil disturbance or smear, and that produces this variation on it. And if we retain that variation, this, this ratio S, we came across it before, but that's that equivalent diameter of the disturbed zone of the equivalent diameter of the drain. And a third scenario that Hansbo examined was the ideal case modified by soil disturbance and modified by drain resistance. And that's what we're seeing here. Okay, the ideal case. With soil disturbance. And with drain resistance. Okay. This would, I'm going to make a little note here. Not routinely accounted for in design practice. Okay. So there are three cases, and let's pursue them now. Let's pursue them in a forensic back analysis of the Vernon case study. Okay. First of all, I'm going to take these field performance data. T90 is 260 days. Here's a relation between U and time. Do you remember all the way back to Fellenius? There's a relation between U and time that he measured, and there was T90 with the drains in the oil drum. Now what we have is T90 at the Vernon test site, and T90 is 260 days. T90 260 days, 100, 200, 260 days. Okay. Field performance, field monitoring. Okay. And these are theoretical curves based on Hansbo's relation. Okay. Theory. U against time, U10 against U20, U30. You can calculate the time for the various, and each of these curves is labeled with a number, and each of the numbers, 1 through 6, and in fact it goes as far as 21 over the page, but they are the cases, each theoretical case that's analyzed, 1 through 6 and through 21. And let's look at these, and this is where the final learning objective is satisfied. And let me keep the same color coding that I had: red for the ideal case, green with soil disturbance, and blue with soil disturbance and drain resistance. So the ideal case would be number 1. Oops. The ideal case would be number 1 and number 4. Why do I say that? Because they don't have any inputs for the smear, the ratio of permeability in the undisturbed to the disturbed zone, and assumed hydraulic conductivity for the undisturbed soil, and the capacity of the drain, the parameters that are captured here and are described earlier in the derivations of the equation and Barron's work. So number 1 is the ideal case, and number 4 is the ideal case. Now, where is the value of C sub h coming from? dE is our spacing in the field, equivalent diameter is the assumed circle, and the coefficient of consolidation, C sub h. We know from lab testing that C sub v is in this range. And we assumed, for purposes of back analysis, that C sub h is twice as large as C sub v. Okay? And that's where that number came from. And if you work with the lower bound number, you get, the upper bound number, the higher number, you get a faster consolidation, shorter time. If you work with the lower number, you get a value not that far off the field data, actually, truth be told. And what we see is then if we modify it to account for smear, if we modify the second one to account for smear, which is a distinct possibility, and we see that in the field, that moves us either to this one or it moves it to this one. And if we add in the drain resistance, makes very little difference, right? The case number 3 and the case number 6 makes very little difference. And that's why, in fact, it's not routinely considered in design practice. So we're really interested in the combinations of ideal and probably ideal modified by a soil disturbance due to the installation. And probably the more structure the soil has, the more smear is going to come into account, and the less structure, I'm thinking of mine waste tailings, the less structure it has, perhaps one could argue, the less that comes into play. So then we did a sensitivity analysis. We kind of knew this is where the goalposts were, and we did a sensitivity analysis. We did a sensitivity analysis to the ideal case. We did a sensitivity to the ideal case with soil disturbance. And that's what would be those ones. And then we did a sensitivity analysis to the ideal case with disturbance and with drain resistance. And that would be the bottom set. Okay. And all of these are modifying the theoretical T90. That's acknowledged that all of these out here are theory. Okay. And all of those curves are numbered and brought out here. And we know that 260 days is our field performance. 260 days is our field performance. And what we were trying to do was to circle in on that field performance. Okay, that's the comparison. It's a little hard to see the big picture, but there's our comparison of theory against field observation. I'm going to come back in and let's hold it. Let's hold it for this. Almost losing you guys. Okay, we're back on our feet here, and this, along with the other ones, are field performance. And I hope what this does is give you a sense of the confidence with which we might be able to achieve or not achieve a meaningful value of T90. Okay. And it turns out, if we look at assumptions of, is the smear zone twice the diameter, 4 times the diameter, 6 times the diameter of the equivalent drain? Is the hydraulic conductivity of the undisturbed soil, is it 3 times? Is it twice? Is it 4 times that of the remolded soil in the disturbed zone? Is if the drain resistance is measured to be this or this or this. And what came out of this loud and clear was that the coefficient of consolidation, C sub H, is the most important parameter. Okay, the single most important parameter. Out of the sensitivity analysis came, and if you want to read through the details, please go to the paper itself. But take it from me that the most important parameter input parameter to design. Okay, and that's what we concluded from our sensitivity analysis. And I've got 2 things I'd like to do in closing off the lecture, and then I'm gonna linger. And thank you for bearing with me here. But I mentioned Tim Stark at the beginning. And let me draw your attention to a case study he wrote in ASCE, published in 2018, I think, is when it came out, if I remember correctly. 2017, came out in 2017. And what happened was this embankment was built with PVD, prefabricated vertical drains underneath it, and the embankment failed. And Tim Stark was called in with a team, I guess, to do a forensic analysis of this. And the key image for me in here is this one. Okay. Here's another plot, degree of consolidation against time. It's pretty much what we're doing here. Okay. And here we see what was assumed for design. This is actually what was mobilized in the field. The C sub H was much lower mobilized than assumed for design. That meant that the time to achieve 90% consolidation was much longer. The time to achieve the gain in strength was much longer. And in fact, the gain in strength was not sufficient to accommodate the embankment loading, and it failed. It failed for a couple of reasons, one of which was the question of the coefficient of consolidation in radial drainage. So that observation from Tim Stark tends to complement the sensitivity analysis here. So that's how I wanted to close. At an executive summary, I would say we've looked at. Let me move back. Let me stick here just for one moment. So we looked at use of prefabricated vertical drains for dewatering mine waste tailings, for accelerating consolidation under embankments. They work like a charm. We have design tools, decision support tools that are long-standing. They come out of Barron's work on circular drains that were sand. They've been transported into prefabricated vertical drains with assumptions of equivalency. Hanspo's equations allow us to do a sensitivity analysis. And if we do it to the Vernon embankment, the key input parameter is C sub H. Tricky to measure, often done so with some kind of a simplifying assumption to C sub V, which we can get from odometer tests. And that's generally the way we do it, unless we did it from some kind of pore pressure dissipation, perhaps with a cone. Those tools and techniques work, but given the geometric arrangement of the drains in the ground, to try and deduce degree of consolidation from measuring pore water pressures would be fraught with uncertainty. Doing so with settlement would be the way to do it. But would I be able to put my hand on my heart and say you can use the decision support tool and with confidence put in all the design input parameters and absolutely nail good agreement between your, between your theoretical calculation and the measured performance in the field? No, you wouldn't. And therefore practice tends to monitor the settlements and make sure from settlements that you're attempting to see if you're getting what you expect as you progress through the consolidation settlement. So that's what I wanted to say about PVDs. Let me acknowledge that speaks to lecture 10. The next lecture, lecture 11, is on barrier systems. And for that, I'm going to post the third and final of the discussion exercises. And I think you know the routine here. I have one to mark. I'll get it back to you tomorrow. But what I ask you to do to inform and be a little bit aware of a number of issues for that lecture, I'm handing out the third and last of the discussion exercise. In fact, it's the last activity to hand out in the course. And I look at two bodies of work. I ask you to look at two bodies of work. The work of Jim Mitchell, Harry Seed, and co-workers when they wrote up the Kettleman Hills slope failure in California, two companion papers in ASCE. And then Tim Stark, whose work that we were just looking at very briefly, admittedly, on wick drains, made 4 recommendations on the use of peak and residual interface shear strength for stability analysis of landfill covers, liners and covers. And they did that in Geosynthetics International. And it's now familiar to you, I hope, but I ask you to describe the nature of the Kettleman Hills failure, very instructive and with hindsight, perhaps relatively straightforward to understand. And then what's the evidence in support of the claims? And with Tim Stark's work, what's the evidence or what's the rationale in support of their recommendations for design? And this will inform an opening discussion that we will have at the beginning of the next lecture. Okay, folks, so let me flip back here. Thank you for bearing with me. we started the lecture, and the experience was the interest was there. Perhaps the hands-on experience limited with wick drains. I hope that I've given you a sense of how you might approach a project, how you might think about it, where and why you might have confidence in certain actions, and where you might place emphasis in terms of acquiring key input data. I could certainly say to you that, and perhaps it be my closing remarks. Can I find it? One of the outcomes of our testing for the mine waste, the tailings, was not only that the filter was compatible with the tailings, but also the hydraulic properties of the tailings that we observed were consistent with those that the designers were going to use. So that was another confidence builder for them. But that's what I wanted to say about the prefabricated vertical drains. I give you the discussion exercise due on or before, I'll pop this in an email, due on or before next week's lecture, please. And I open it up now if anyone has any either questions related to the lecture or observations or comments to make. Once again, if anyone needs to disappear off, I understand entirely, and please do so. But notwithstanding that we just squeaked a little lengthy in the lecture, my apologies for that. But if there are any questions, I'd be delighted to handle them. Oh, yeah. Yeah. Mm-hmm. Right, right. Well, we'll call that one a kind of a complementary question. I'll answer it very quickly just to move things along, and then we'll return to the main PVD one. Ordinarily, we're going to have to design a dam for three major risks. One is slope stability. The second one is internal erosion, and the third one is overtopping, and we don't want it to overtop. Ordinarily, we would put in a spillway. Not all dams may have a functional spillway, and you may have occasional dams that really aren't intended to be overtopped. They may be sitting. If you think, you may have valley systems and saddle dams. They are helping maintain lake levels, but they're not the lowest point around the perimeter of the reservoir. So it may well be that, given the way a reservoir system is intended to work, that you may have occasional dams that do not have a spillway associated with them. And it could, on occasion, it would be rare and not fully desirable, that the dam is designed to be overtopped without failing. But I'd say that's highly undesirable. But you could have a scenario where you have a dam. I would expect it to be a relatively small one, and I would expect it to be part of a sequence of dams where its crest elevation is larger than others in the system. And thus, the expectation that it would ever be overtopped is negligible. And that would be my first stab at an answer to that question. Yeah. Any other questions related to the PVD? It was a broad sweeping presentation, but if there are any either questions of clarification or things that don't just seem to add up, I'd be delighted to speak to them.
I had a sort of a less technical question, but do you have a sense of maybe like a rule of thumb kind of cost per meter for PVDs? It's something that we always struggle with.